My name is Teresa and Steiner, and in this video I present my paper, Differential Privacy for Approximate Pattern Matching. I will start with defining the problem, step by step. So first, I'm going to define what a string is. A string is any sequence of symbols from a fixed alphabet. It can be used to model any kind of sequence, for example, DNA, sequences of events, or really any kind of text data, really. In this example, S is a string, and it represents the text Batman and Anna sing Nana Nana. So one of the most fundamental problems in string algorithms is the pattern matching problem. Here, one is given one long text and a short text, which we call the pattern, and the goal is to report all occurrences of the pattern in the text. So in this example, where the pattern is NA, the pattern occurs 5 times in the string S, and we mark it in red in this slide. Now, going back to our initial examples of what a string could be, we see that this could include highly sensitive data. So in this work, we want to study if we can solve pattern matching while protecting differential privacy. Next, we will define our privacy model. So this here is the standard definition of differential privacy. A randomized algorithm is differentially private if its output distributions are similar on datasets that differ only in a single data point. By similar, we mean that they differ in at most a factor e to the epsilon, where epsilon is a small constant. To define differential privacy for strings, we then need to define what it means that they differ in one data point. In the definition we use in this paper, we define this as 2 strings differing in one position. So this means we want to have close opposite distributions for strings that differ in one position. In the pattern matching problem, we consider the case where we want to keep the long text in which we search private, but we don't care about the privacy of the pattern. So we assume the pattern is known to the data analyst, and we want to find out some information about the long text in relation to the pattern. So in our previous example, where a string modeled sequences of events, this definition then means that a differentially private algorithm does not reveal too much information about any single event. Thus, this definition also corresponds to the so-called event-level privacy, which has been studied in the continual observation setting of differential privacy before, in case you're familiar with that. In this work, we study a variant of the classic pattern matching problem, which is called the K-approximate pattern matching problem. Here, the goal is to report all substrings of S with a distance at most k to p. This is a well-studied problem in string algorithms without privacy, since most of the real-world data is noisy. So the goal is to still be able to report patterns in the text, even if some mistakes might be introduced for some reason. So here we have an example again, where our string is again Batman and Anna sing Nana Nana. Now the pattern is P, and we want to find all occurrences of P in S with a distance at most 2. So that is the number of positions between the occurrence of the pattern and the pattern should differ by at most 2. So if you look here, we have the occurrence here, starting at the G in sing of banana, which differs in the 2 first positions. Then for Nana Nana, we only differ in the first position, and again, there's another Nana where we differ in the first position. So this problem allows some noise on the matching. However, the noise here is deterministic. So I want to report all occurrences with distance exactly at most k, so exactly k or lower. However, to be able to study this problem in differential privacy, we need to allow some random slack. So we define a version of the problem with a slightly weaker accuracy guarantee, which we then want to study under differential privacy. So with high probability, we still want to be able to find all occurrences of distance at most k. However, we also allow to report some extra occurrences which have a slightly larger distance. And we call this slightly larger distance, so the difference between that and k, the error, and we measure both a multiplicative error gamma and an additive error alpha. We also studied the counting and the existence version of this problem, so where the counting version is defined in the same way, but we don't need to report all such occurrences, but only count them. And in the same way, we define the existence version, where with high probability we answer yes if a substring of distance at most k exists, but we may answer yes if a substring of a slightly larger distance exists. For both the counting and the existence version, we also want to return a witness. So we want to return one substring of distance at most 1 plus gamma k plus alpha if we return yes, or if we return a non-zero count. So the goal of this work was to analyze which values of alpha and gamma are necessary or sufficient. So next I will summarize our results. First, for the existence version of the problem, we give an algorithm with no multiplicative error and a log n additive error. N is the length of the text S. For the counting version, if k is at least log n, we get a multiplicative error of log n. Else, if k is smaller than log n, we get an additive error of log squared n. Both the results for existence and counting hold for all possible patterns. For certain patterns, we get an improvement over this. Specifically for patterns which are close to periodic, we can show an algorithm which answers reporting with only a constant multiplicative error and a log n additive error. Now it might seem that log n is already very large as an additive error, because n was the length of the long string S. However, we also show a lower bound saying that an additive error of at least log n is necessary, even for the existence version. So it also holds for other versions of the problem, and this lower bound holds for all patterns. Now for the rest of this video, I will give an overview of the main ideas behind our upper bounds. For those of you familiar with differential privacy, you will know that the sensitivity of a query is an important notion to define differentially private algorithms. The sensitivity is a measure of how much the value of the function we want to compute changes, if I change a single data point. And specifically, it's the L1 sensitivity is the maximum L1 norm of that difference. Now, the number of positions that two strings of equivalent differ in is called the Hamming distance. You might notice that if we could compute the Hamming distance between our pattern P and any substring of S of the same length as P, then we could immediately solve all the problems that we consider in this paper. However, while the sensitivity of computing the Hamming distance between one substring of S and P is 1, the sensitivity of computing the Hamming distance between P and all substrings of S of the same length is as big as the length of P. So this means we cannot use a simple mechanism like the Laplace mechanism immediately to solve this problem. Instead, we use a different technique called the sparse vector technique, which was described, for example, in the book by Dwork and Roth. So this technique allows to ask as many sensitivity Q queries as we like, but only report the first query answer, which is approximately below a threshold. By approximately here we mean again that there could be an additive error. And this additive error for the sparse vector technique is logarithmic in the number of queries that we ask. This already gives us an algorithm to solve the existence version of our problem. As I said before, computing only the Hamming distance between the pattern P and one substring of S has a sensitivity of 1. So our queries are just computing the Hamming distance between the pattern P and one substring of S. And then the substring changes. This will give us multiple queries. So for solving existence, we only want to find one substring which has a distance at most k or slightly larger than k. So what we do is we set our threshold for the sparse vector technique to something slightly above k, so that we can guarantee that if the distance is at most k, then with high probability we will report the substring, and we will only report substrings which have a distance that is not too much larger than k. So again, one query is computing the distance between the pattern P and one substring of S, and we slide the substrings of S that we consider from left to right. And since we ask at most n such sensitivity 1 queries, the additive error will be at most epsilon to the minus 1 times log n. Next, I will talk about some periodicity properties of strings which are needed for a solution for the counting and reporting versions. For this, we first look at a slightly larger pattern which is close to periodic string. Banana, Rama, Sana. It is close to the periodic string of period 2, which goes nana, nana, nana. Thus, at every second position in the string nana, 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 there is an occurrence of p with distance at most 4. The argument that we need is sort of a reverse engineering of this property. It basically says that if we have two substrings of S which are close to P, and P is close to periodic string, and they overlap by at least half the length of P, then the entire string spanned by those two occurrences is close to periodic by a recent result from Fox, or 2020, sort of recent. So this then again means that we immediately know that at every period there's another close occurrence of the pattern. And this is the main property that we need for our algorithm of the periodic case. So next I'll describe our algorithm for the periodic case. We start by dividing the string into substrings of roughly length 3/2 times the length of P. And we consider each of those substrings as a separate subproblem. For each of these subproblems, we run the existence algorithm, once from left to right, until we find a close occurrence, and then we stop. Then, as the next step, we scan from right to left, and stop if we find a close occurrence. Now, if both algorithms found an occurrence, then because the string we looked at was of length only 3/2 times the length of P, they have to overlap by at least half. So we have this property. So basically, once we found two occurrences which overlap by at least half, I don't even need to look at the rest of the string to know that there are close occurrences at every period in between. So to summarize, this is our full algorithm for the periodic case. We first divide the substrings into lengths of roughly 3/2 times the length of P. Then we run the existence algorithm once from both ends. And if both of them find an occurrence, then we report all periodic positions in between. Lastly, I'll quickly give the main insight we use for the aperiodic case. In the case where P is not close to a periodic string, there's another result from the same Fox paper, which gives us a way to bound the number of occurrences of P in any substring of length at most a constant times the length of P. We then again divide the string S into smaller substrings and use this property. I will not go into more detail here. Instead, I want to mention another important detail, which I just glossed over a bit before. So for both algorithms, we divide the string S into smaller substrings and consider them as independent problems. Why can I just do that without further privacy loss? The reason is that the way we define our subproblems, at most a constant many of them overlap, which then means that if I change one position in the string, it only affects a constant number of subproblems. And this means that we only need to use what is called sequential composition on those subproblems, at most a constant number of subproblems, and can use parallel composition for the rest. I want to finish by mentioning some possible directions for future work. First, our results still leave a gap for the counting and the reporting version of the problem. Second, in this work, we consider the Hamming distance for both the definition of the approximate pattern matching problem, but also for the privacy definition. For both of those, one could consider other distance functions, for example, the edit distance. Lastly, there are many more string problems which could be interesting to study in the differential privacy model. Thank you for your attention.